In this video, I'll give a few examples of some different molecular geometries of some molecules as well as some molecular ions here. I'm going to be using the VSEPR model. That's VSEPR. And you're saying, hey, that spells VSEPR, not VSEPR. But we have to put it in that order because it stands for valence shell electron pair repulsion. And the electron pair is really the big deal. Well, I could talk about electron pair. It's all important, but the electron pair, because we'll see where we place those on these Lewis structures of the molecules. Zinc, I'm going to start with zinc dichloride. And the reason I'll start with that is because that's the most basic. That will be a linear geometry. So just straight across, we've got a zinc in the middle, a double bond to Cl on one side, a double bond to chlorine on the other side, and we have some remaining lone pairs. And what happens there? Well, the electrons in the bonds and the electrons in the lone pairs, these are all repulsing each other. Remember, this is electron pair repulsion. And so they make a 180-degree angle, or just some straight line, a linear shape of this molecule. So this is a linear molecule. Now, the next one I'm going to go to is the NH2 minus. Notice that this is an ion. So this is going to be bent, and not just because it's an ion, but I'll show you. I'm going to draw it, and then I'll explain why it's bent. So before I draw it, let's talk about what this negative charge does. Well, that tells us that we have an extra electron, right? We had 5 valence electrons from nitrogen plus 2 hydrogens times 1 electrons per hydrogen atom, or yes, and then plus the 1 electron. So that equals a total of 8 electrons that we have to worry about. Well, with these 8 electrons, then here's what we're going to do. We have nitrogen right there in the middle, but instead of putting hydrogen on either side, left or right, we are going to have these lone pairs up on, sitting on nitrogen, and those are going to push. Those are going to push those bonds down like this, which is why this is called bent. Okay, so these lone pairs repulsing the bonding pairs that we have between nitrogen and hydrogen, so bending this. Still in the same plane, still two-dimensional here. And I'll finish this. Typically, these are drawn with these balloons, highly technical term, balloons, around the lone pairs, and that tells us that this is being bent. Next, I'll stay two-dimensional with aluminum trichloride. That's AlCl3. And that is trigonal planar. Trigonal. And then we are told that it's all in one plane by the word planar. Now, in a trigonal planar Lewis structure, we have aluminum in the middle. I'm going to change colors so we can see this a little better. We have aluminum in the middle, and we have 3 chlorine atoms. But guess what? We're going to put a double bond there, and I'll talk about that in just a second. I'm going to put all of the important electrons, the lone pairs there. And each chlorine atom has 3 lone pairs. So we have all of our valence electrons taken care of. Now, what's happening? You're thinking, hey, this is a double bond, so shouldn't this be pushing those away in some harsher fashion? Well, this has something called resonance. So what that means is that this double bond is shared among all 3 of these bonds. So kind of, you can think of it as playing the field. It's moving around all the time. So this has resonance. So it's not that one atom has the double bond more than the others two. Well, that pushes all three of them equally apart. So we have this 120-degree angle, still in the same plane. And for the climax, the big hurrah, we have aluminum AlH4 minus. So this is another ion. So we've got 8 electrons, 8 valence electrons to worry about. And that's going to be taken care of with just four single bonds. So you could see it as, oh, okay, we'll just put our aluminum in the middle, and you've got hydrogen up here and hydrogen down here, and hydrogen and no lone pairs on the hydrogen. So hey, what's wrong with that? Well, it turns out that these things are all pushing, all four of these are pushing on each other equally, and so they won't. The best way for this to organize itself is not in a two-dimensional, but to get as far apart as possible is actually in a three-dimensional model, and that's this. That's what I'm showing here. So this is the real picture that's very difficult to draw two-dimensional. So I pulled up this graphic, and so you can see these hydrogens out at the tips here and aluminum right in the middle. And this is called tetrahedral. Tetra standing for four, and hedral, sides. So four-sided, and that's what it looks like. The aluminum in the middle, surrounded by hydrogen atoms. There were some good examples of molecular geometries. There are plenty more, but that was a nice introduction. I hope that was helpful. If you did find this video helpful, consider liking it or sharing it with a friend.